Good morning to everybody, and today let's start with the exercise number 4, the lab number 4. And this lab number 4, as you will see, we'll enter in a new topic that is related to our software that in the meantime you see I'm launching. And basically that lab will regard the ability to change the distribution of data, and therefore with a way to understand in a quantitative way how are the characteristics of the data. So we did open the software, and you remember we did save different views, but however we will start over, and as usual we are working with Landsat data. So from the next time maybe we will change, and you see as usual we are opening the file in the main menu, open as optical sensor Landsat GeoTIFF with metadata. All right, in this case, I'm going to the folder that contains the data. In this case, you see here data. We are going to the northwestern Italy, and this time we are using last time we used Landsat 8, now we are using Landsat 7. So let's open this folder, and let's open the metadata text file, and let's open it. All right. You see, you remember that we have displayed the image in the visible, a particular scale with a certain zoom factor. I can take my data manager. You see, I can see the characteristics of the different data sets we have loaded. And you remember that we have 3 different data sets, the reflectance 1, the 2 that are related to the thermal bands, and the last one, the band 8, that is recording a very high resolution, geometric resolution data in a panchromatic mode. So, so now we have this data. I can zoom out, for example, in order to let's understand where we are. So you see, today, now we want to understand how these data are organized and which are the characteristics of this data. In order to understand how these data are statistically distributed in every single spectral bands. So we would like to understand if the digital number that is reported within each single cell, how it can be represented, and which is the property of every single digital number in a general distribution of the data. All right, so let's close the data manager windows, and the operation we want to do is start from the layer manager and having this color image. I remember that this is the visible because we have that in the preferences. Let's right click with the mouse, and for example we can see here the metadata. So so we can start to go in depth in this way. So let's describe these windows because it's extremely useful. And you see that in left part of these windows we have the name of the file with a whole series of different other information concerning details and metadata that I remind you, they are metadata are the descriptors of the data itself, of the different bands, the acquisition data, and whatever. So the first descriptor concerns what is called raster, and back to the drive us back to the characteristics of our data set. So the position, the physical position in the memory. Yep. Then we have the dimension in byte. You see that is something like 350 megs. The format. And then what is very important is the size in row and column of the image matrix. So I want to remind you that the origin of the representation system is upper left, and the axes are rotated. So actually column are rows and rows are column. So you see these are then the 6 bands of the data set that are big as more or less 8,000 for 73 hundredths of dimension. Then you have here, you have the interleaved that we saw in the lectures. The interleave, you see, is in this case is BSQ, stands for band sequential. Band sequential means that all the bands are stored in one single file, and every single band is stored one after the other. All right, so this is described in the lecture number 8 or 9. I don't remember explicitly. So that means that in this case, you see, the data is stored in byte. Byte means that all the data are stored, the digital number are stored in values in 1 byte. That means that are ranging from 0 to 255. So that means that all the digital number, the total number of digital number is columns times rows. So that means that we have more or less 60 million of data. So they are stored in BSQ, so in band sequential. So at the beginning we have the first band, and at the end of the single file we have all the digital number ordered of the 6th band of the mid-infrared. So you see, we have also the data ignore value that in this case is 0. That means that you can get rid of the background. You remember we have a background that is fixed to 0, that in reality is black. So we can get rid of this value in order to process that as transparent. So in order to change that, it's always possible to see here, edit metadata. So we can change this metadata, and clicking this metadata editing, see, we have this new window where we can change all this information that we saw before, and we can change it. Pay attention, because obviously there are information that are absolutely necessary to be able to read this file from the moment that the file is this raster name that contains 6 band and is written sequentially in BSQ, so it's not organized in another way. So that means that if you are changing, for example, the number of columns and number of rows, I mean, the data will be read in a different way, and that way will be not the right one. So you see, if we are changing this number of columns or rows, we could read the file in a wrong way. And also, of course, changing the number of bands. And it's quite obvious here. So you see, here we have the different interleaved that we saw in the lecture, the BSQ, BIL, band interleaved by line, and band interleaved by pixel. And you see, these 3 possibilities are related mainly, as you see, as you know, by the lectures, by the theoretical part, related to the kind of sensor that is acquiring this data. For example, the BIL, the band interleaved by line, is typical of push broom scanner, while the BIP, this one, the band interleaved by pixel, is typical of this particular sensor, thematic mapper mounted on board of Landsat, because it's acquiring one single cell after the other. So I mean, as you well know from the theory, are based on this kind of multispectral scanner that is acquiring the data. So I mean, typically they are related to whisk broom or push broom scanners or frame camera. Of course, I mean, this data, for example, this Landsat data is originally acquired in a band interleaved by pixel format, and then is converted in BSQ just to be more easy to use also for other users. All right. All right, so then you see we have the data type that is byte, 1 byte for every single cell, in this kind, we have a byte, but you see we have a bunch of different type and characteristics, type of data that we can store. And of course, for byte, the radiometric resolution is ranging between 0 and 255. This is the format of the file. This is the acquisition date. And you see we have also the data INO value, that in this case is 0, that is allowing us to see the background as transparent. So I'm closing these windows, and you see, this is the transparent part. As you see, we have the frame that is containing all the image, but having this 0 as don't consider the background value, in this case, you see, is something that is transparent. So why is it rotated? You see, of this angle, is rotated for the effects of the georeferencing operation. But we will talk that of this rotation when we will talk about the georeferencing method. So, yeah, in order to represent this data, of course, if rotated, we need to inscribe all the image in a bigger frame, and so you know all this background is necessary in order to display the image, but we are ignoring that because eventually they are not data. So let's go again to the metadata, all right, just to have more information. So for example, if here in mapinfo, we don't have many things to do except from the facts that the value upper left, the position 1, 1 of the matrix had these coordinates. This is the upper left point of the image, and the pixel size is 30 meters, and the units of measurement is meter without any rotation. On the coordinate system, we have already seen basically that everything is oriented and reprojected according to the UTM system in the 32 fuse. And you see this is the ellipsoid, the WGS 84. I'm sorry. And here we have all the parameters related to the projection. Okay, for the extents, you see we have the size of the maximum size of the image, in where we have the upper left position of the corner and the lower right corner with the couple of coordinates. So we have the border of the frame we are using. From the spectral point of view, you see here we have the description of the individual bands with the conventional name of the bands, where in the first column we have the wavelengths, the average wavelengths of the acquisition interval. This FWHM is basically refers to the spectral accuracy in this case. And then at the end, you see, we have gains and offset that are these two values, the offset and values, refer to the possibility to calibrate the image, passing from digital number to radiance value, real physical values, that this radiance value will be used for all the information, and these values of gains and offset for every single bands are the values that we have already defined the theoretical part in order to calibrate this data, and so to pass from a digital number in integers, from 0 to 255, to values. And here you see we have also the irradiance value here. What is the irradiance value? You know from the theoretical part, is the quantity of energy that is striking over the surface at that particular date in that particular wavelength interval. So, for example, in this blue part, we have more or less 2,000 watt for every single square meter. And you see that going to larger wavelengths, the irradiance is decreasing. So, for example, in band 6, you see that we have, that is conventionally called band 7, that is the near infrared, in which the irradiance value is very low, because you know that from the emissivity laws, the sun is emitting very low energy going to larger wavelengths. So we have a peak of emissivity in the visible, in particular in the yellow dominant, and starting from that point, there's a loss of irradiance that is due to the decreasing of emission from the sun. All right, so you see that these data are very, very important because they are strongly related to what we defined in the theoretical part, especially talking about the Planck laws and all the other things. So, okay, let's go to the image parameters. So you see these are very important, especially for the azimuth and for the sun elevation, because in this case, in September 28th of the 2002, the elevation of the sun at that moment during the acquisition, and the time you see is 9:58:52 seconds local time. That means that we have 1 hour more, so it's around 11 o'clock, all right, so 10:58, because this is a local time, Greenwich time, so we have the legal hour in Italy. So around 11, the sun elevation was of that quantity, 40 degrees. The security, you see, there's the unknown label, so you can also change that in order to make safe your data. And then these auxiliary, the auxiliary errors that are the pyramid files that are being created when you are opening the image. This is simply a system definition that is speeding up the possibility to visualize your data. And especially when you are zooming in and zoom out, you see that it's very continuous, this zooming operation that is essentially thanks to this pyramid with images in different resolutions that are stored and that are pre-saved in order to speed up and to make continuous, for example, the zoom or the pan that we are using when browsing the different images. All right, so we can close these things here. So we saw all this metadata, and now we are going to check the numerical part of our data. Hence the problem we have in this moment, after having seen all these different metadata, is to begin to verify what are the characteristics from the analytical and numerical point of view of our data. So in order to do that, we can go to the layer manager, on the name in the multispectral example, right-click having the pop-up menu, and then you see we can go to the quick stats instruction. Quick stats is begin to perform some operation. You see that it is evaluating, is calculating something in order to present you with temporary files that will be erased when you will log out from the software. And you see this processing is due for having these windows, you see? Maybe for your first time, it takes more time than in my case, because I already done that. But you see in these windows that we have these are very important windows because it allows to observe carefully these are the characteristics of our data. So in these windows, you see that in the top of the windows, we have the name of the file. This windows is called statistics view with a reference to the name of the file. So you see, we open this metadata file, and so the statistics windows has been made over this file. This statistical windows actually is analysis of the characteristics of the data of the image matrix in the different spectral bands. Generally consists of three parts. A top windows here, where you have a graphic display, and a window here in the bottom where you have a reference, a tabular reference to the data that is graphically represented in the upper part of the windows. And then a third window that in this moment is not visible, but you can open with this arrow. You see here where we have some more tabular information that allow us to basically check the graphic windows in the left part. Let's close that. Let's work on these first windows. In particular, I want just to analyze the tabular part of these windows. And you see here there are tables that are relatively long and allow us to verify how the data are distributed. So let's start with the first table. You see basic stats here. In basic stats, we have presented our 6 bands representing the multispectral data sets, and that is recording reflectivity, in which the bands from 1 to 5 are those, while the band 6 is essentially the band 7, because it's a convention. You see, in the next 4 rows, you have extracted the 4 main statistical value, and this is the first time that we saw, but we will face them many times in many other operations. And for every individual bands, consider that we are working with digital numbers, that is the distribution of the digital number in our image matrix. For every single matrix, all the values are extracted here, the minimum, the maximum, the mean value here, and the standard deviation of this data for every single value. These are the 4 values that are extracted. How larger is the population of this data? You remember, is typically the dimension of the image matrix that you remember is something like 8,000 by 7,000. So more or less 60 millions of data. And so all these statistical values are calculated for around 60 millions of digital number for every single spectral bands. So for every single 60 millions, we have extracted minimum, maximum, mean, and standard deviation of the data for all the 6 different bands. For these basic stats, you see, we have a graphic representation. You see here in this diagram that is very typical. And these are the diagram where on the x-axis, as usual, we have the variation of wavelengths that are representing our different wavelengths from 0.5, 0.6, 0.7, blue, red, and green, you see here. Then we have the near infrared here, and here we have the near infrared, the mid-infrared. On the y-axis, we have our digital axis ranging from 0 to 255, because all the radiometric resolution is 1 byte. And in 1 byte, you can store only 256 different values ranging from 0 to 255. So you can see here that in this case, this representation is what is represented in the tabular form. So here we have the single bands on the x-axis, and with the different lines in colors, you see in black lines here is the mean value, with green lines, we have the standard deviation, plus and minus in comparison with the mean value. So I remind to you that the standard deviation is the divergence from the mean value, from the calculated mean value. And so usually is a symmetrical distribution in this case. And then the two other red lines are the minimum and maximum of the distribution. All right, so in this case, we have the representation, the graphical representation of these values. If we are going in the part below here, you see we have the histogram of band 1. What does it mean, histogram? That means that we have tabulated for every single digital number, and this is starting from the minimum. You see the minimum value in band 1 is digital number 3. So you see we have a series of records, so from 3 to 255. For every single digital number, you have the counting of the cell that has this particular digital number out of the 60 millions of cells that we have in the matrix. So how many cells have this particular radiometric value? So the frequency of the digital number ranging from 0 to 255. And this is the counting, of course, of how many cells have this particular digital number. Only for the number 3, we have, in 4 and 5, we have also 1. For 6, we have no cell that have this particular. This is the total this is the cumulative value. So you see that is added for every single row. Here we have the percentage calculated, and this is the accumulated percentage of the value. You see that going ahead, you see that the low value, they are represented by a very small quantity of data, and this data are getting more, you see, when you are passing through higher value. You see that ranging from 43 to 46, we are ranging from some hundreds to some 100,000 of values. So, for example, you see from 43, from 7,000 to more than 100,000. So you see, there's a very high frequency in particular digital values that have many cells represented, so a very high frequency. And you see that the peak of frequency, we can check which is the peak of frequency. Let's check it. That, I mean, we have the peak of the frequency. It's more or less in 58, you see, that we have more than 2 millions and a half values. That is the peak of the distribution. So I mean, the peak of the frequency of the digital number is around the digital number 58. So this is limited to the band 1, of course, because we can also have the other thing. So what we can do? We can obviously change the values here. For example, if we are going here, in any way we can localize the stats. For example, now we have a histogram of band 1. We can have the histogram of band 2. So you see? So here we can change the tabulation of the bands, in which, for example, I can use, for example, band 4, and you see we have the distribution in a tabular form of band 4. All right? So we are starting from band 1, and we add band 2, and now we have band 4. So when you are selecting that things here and localizing the stats, you are adding to your tabular part of these windows. Okay, then we have these things. You can select all the values. We can clear, of course, the selection, and we can copy that to clipboard, for example. You can take these values, you can copy that, and for example, you can select, you can put that in Excel, in a text file. And then the reporting precision is the precision that you are using in this case. So 6-digit after the commas, you see. If I'm changing that, I can use only two different digits, and that's enough in order to represent all this data, because I mean, the accuracy is enough for these things here. All right, so for this part of the window, so for the diagram, we have the opportunity to represent the horizontal with an index. For example, you see here 1 to 6, that is the conventional numbering, to measure that in wavelengths, for example, or in wave number, for example. So in frequency, in this case, for example, or in centimeters, all right. So we are not using that for example, in that index, we can use the index in order to have the band. The data value, you see, we can have also continual removed, so I mean in percentage, in normalized value, or also with binary encoding, for example. But I mean, we need that in data value. We can also stack the plots. For example, here I have more plots for the different bands, and we can also reset these plots, of course. So here we have to import from ASCII value, if we have, for example, it's never happened, or taking that from spectral library, we will talk about that later on, to export this data in different formats, for example, in PDF, in image, to copy, to print, to put that in PowerPoint, and so on. Or also the possibility to go to the option, and I want to spend more time, but because you have many different options. But what is very, very important here is the possibility to select the plots. So you see here that you see we can take into consideration these statistical values, but also the histograms we can use. So for example, if I'm taking the maximum, minimum, and mean value, I have this representation, you see, for the value of the different bands here. So in black, the mean value, in green, the standard deviation, and in red, we have the minimum and maximum. And we can have also the possibility to see also only the standard deviation, for example. You see, and in this case, the standard deviation is changing a lot in the different bands. So you see that for the first two bands, the standard deviation is very high, while for example, I forgot to say that if you are clicking with the left button of the mouse, you can point out here and to measure the coordinates. So for example, here, left clicking with the mouse, in the first band, the blue band, the standard deviation is relatively low, for example, 25.39. In the green bands, you see, is 25.91. In the red band, it becomes 31. In the near infrared, it's much higher than the others, and is decreasing, for example, in the mid-infrared. So you see, on the variation of the standard deviation, and consider the unity of measurements. So we are taking into account only variation comprises between 25 and 31. So there are not so big variation. So take into consideration the scale here. But we can understand from here that the standard deviation is higher in band 4. And these things here has a very physical explanation that, for example, here there are very high values that are coming from the vegetation and very low values that are coming from the water. So if I move in that, you see, we know that in the in the vegetation here that is representing most part of the vegetation. So water and vegetation are the two more represented surfaces in this surface. Here in the band 4, the standard deviation is higher in band 4 because it comprehends vegetation and water that are reflecting in two very opposite ways. Very high in the vegetation, very low in the water. So that means that the higher standard deviation in band 4 in the near infrared is due to this fact. While, for example, in the visible, for example, in the green band, the standard deviation is lower because, I mean, all the values are more compressed to the mean calculated value. Because, I mean, you see, water and vegetation are sometimes grayish in the same time. Because you see here, when you see here in the visible, the image is not so much contrasted when you see water, the difference between water and coastline, differently from, for example, a false color image. All right, so very important things here that we need to analyze is the other possibility that in the select plot, we can look at the histogram. So, for example, let's try the histogram of band 1, and you see the histogram is not the graphical representation of what we saw before. You see, we have on the x-axis our digital numbers ranging from bands 1 from 3 through 255, and on the y-axis here you have the number of cells, that is the column count in this here. So how many digital numbers, so how many cells have this particular digital number, all right? So this is a fundamental aspect, and I'm enlarging these windows in order to look at it better. So this histogram, as we know from the theory, is very important because it's representing the statistical distribution of our data. Therefore, very far from having a uniform distribution that could be represented in this diagram as a straight line parallel to the x-axis, where all the digital numbers are equally represented within the image, you see that here we have a very completely different distribution. So in this case, we have a curve that is representing this distribution that, I mean, this curve is for low values here, from here, you see, also here we can left click with the mouse and we can check which is the value of this particular digital number. And so that means that digital number 19, we have only one single cell, and in brackets at the beginning of the test file, we have the accumulated frequency. So that means how many cells from 0, from 3, from the minimum value, till to 19 are represented. So you see there are only 17. So if I'm moving, you see, till to the value for 41, 42, we have very, very few digital numbers. So, for example, here in 41, we have only 39 values in the accumulator. Then you see here is we are going to the peak, and the peak you see is 57. I'm sorry, 59, in which we have more than 2.5 million value represented. So that means that this particular distribution is a very particular distribution, and as we know from the theory, is typical of a log normal distribution. That is a curve that is very similar to a Gaussian, to a normal distribution. So it's an inverse of the normal distribution that is related to a normal distribution that is characterized by having a very narrow bell, you see here. And so we know that from the dimension of the bell is measuring the contrast of the image. We know that from the theoretical. We have a maximum of the distribution, and it has an asymptotic behavior for very high values. So you see, all the values, for example, here, 106 to 255, are represented by very few cells of the images. And this is very typical. And there are very few cells that have values more or less 100. All right, so like all the values comprises between 0 to around 40 are very underrepresented in the image. You see here in 42, we have very few values. And you see, I mean, these asymptotic values representing a very low values of digital number and of course of cells of the image. So we said the size of this bell is basically represents the contrast and gives us the measure of the contrast of these bands. And so it's not representing anything else that the log normal distribution has this property that the maximum distribution is more or less very close to the mean value of the calculated mean value. So you see here the maximum is 59, for example, 59, and you see that the mean value is 66. So I mean, you see, it's quite close to the value. So the maximum of this distribution is more or less very close to the mean value. And the position of this curve along the x-axis, so if I move in that, is giving us a measure of the luminosity of the image. So you see that being this curve very close to the y-axis, this image is dark. And due to the fact that the valley is very narrow, it's also very low contrasted. So what we want to do for this content using this histogram is, for example, to modify contrast and luminosity. Because, I mean, having improved contrast and luminosity, we can observe better the things. So we can also observe other bands. For example, the histogram of other bands. And you see that the histogram of other bands is quite different. And you see here, we have this kind of distribution. If you are choosing band 3, you see, this is the histogram of band 3. So considering that these images are represented essentially water and vegetation, and considering that the vegetation is reflecting very low in the red and also the water, you see that the blue line, that is the band 3, the red band, there's very low value, because in these particular scenes, there are surfaces that are not reflecting. For example, band 4, you see here, band 4 is very different. There's a particular distribution, it's a bimodal distribution. This is the first peak of the band of the near infrared. In this particular digital number, you see here, it's 15 values. What is this peaks of distribution? It's a water, of course, that is reflecting very low. And then we have here another peak that is, I'm moving that, I'm sorry. So this is the maximum, is more or less in the 99, 100. What is represented these values? All the vegetation, of course. So in this case, in band 4, we have a bimodal distribution, because, I mean, in this case, we have two different textures, the two different surfaces. And you see that the other distribution of the visible are more or less similar, while for band from the near infrared, we have a very different distribution. So you see, starting from blue, red, and green, I mean, there are very similar histogram distribution, apart from the position along the x-axis, for example. But while for the band 4, I mean, it's completely different. Let's check also the band 5. You see, band 5 is similar to band 4. So again, water for low values in the mid-infrared and peaks in the vegetation, but lower than in the near infrared. Let's check the band 6 that eventually is band 7. But you see, is similar, but for the vegetation, I mean, we have very low value. So from these different histograms that we have overlapped, we have, I mean, we know that the three bands of the visible is very similar in these scenes, of course, in this image and representing this particular part of the world. But I mean, it's more or less regular also for the other acquisition. While for the other infrared bands, there's a sort of similarity. So I mean, we have two different bunch of histograms. The visibles, so visible bands have a very similar distribution as the near infrared, and this distribution is different from the two groups. So we solve these histograms, and you see we can overlap these different histograms, and we can see that also from the tabular point of view. All right. Obviously, is more synthetic to see that in graphical. If we are opening that, you see, now we have the visibility, and you can check out, and we can see only one particular, you see, histogram. So this part of the windows is used for control the representation. All right. So, for example, in the infrared, I have here. This is a cyan that I don't see anything, so I can change the color, for example, of the representation. So, for example, I can represent that in red, you see? So I can change the colors of every single diagram, and I can change all the graphic properties, the kind of symbol lines, the line depth, and so on. All right, so this is an extremely important topics of our labs. So let's go to the file. We can export that to the text file, all this data to the text file. All right, and of course you have always the online help. I'm closing these windows because now we can perform another operation. Now we can finally use our functions here to modify the brightness or the contrast. In order to better understand these things, let's activate the data manager, all right? And let's use and let's open the band 4 in grayscale on the same view, all right? So this is our band 4, that is the near infrared. So, and let's open again the band 3 in grayscale mode in a new view. All right, here you are. All right, I'm closing data manager, so you know, I'm selecting the frame, the cyan frame. I'm going to this view. I'm moving that to the center. Then maybe, and I can view and I can link the views from the view menu as usual. All right. So we have the two bands here. On the left side, we have the band 4, the near infrared. On the right, band 3. You see that immediately see that these two bands are completely different. So if we want to represent that in terms of contrast and brightness, so repeating, having these two bands, a particular histogram, because every single image has a particular histogram, but it's not a transitive property, because every single histogram can represent more than one image. Of course, you can have the same histogram for completely different areas. But in this case, these two images have an histogram. These two histograms are different, of course, and we saw that before. This is the near infrared, and this is the red band in the visible. So having these two histograms, if we can judge that, the red band is darker than the near infrared, you see? So this distribution is close to the origins of the diagram, to lower digital number values. And I need also to admit that the red band is less contrasted than the near infrared one, you see here. All right, so that means that as we seen before, that the bell of the distribution is narrow in the red band with respect to the near infrared. So statistically speaking, that means that the maximum of the distribution of the red band has lower values than the near infrared. So the red is darker than the near infrared. The standard deviation of the red band, so the divergence from the mean value, is smaller in the red band than in the near infrared. So that means that the red bands is less contrasted than the near infrared one. All right, so let's select in the layer manager the red band. So you see here, we never talked about that before, but here below, in the main menu, we have the possibilities, you see, for example, to improve the brightness, that in this case is set to 50, to the center of the distribution. You see, if I'm moving towards a higher value, I improve in the luminosity. You see, for example, 82. You see that the image is brighter. So moving this bar means simply to have taken the histogram of the band 3 and to translate that to higher values. So that means improve the luminosity along the, moving that, shift that along the x-axis towards the right part of the diagram. So moving that to higher value. So you can understand that having also numbers, I can force that to a particular position. For example, I won't put that to 75, I can put 75, and then you see, I press enter and you see that it's changed. So here we have 82, now we can put 82, press enter and you see it's changed. The second bar is the contrast. So pay attention here, that here in the brightness, you can reset the original brightness. This is these icons, in which you can reset the brightness to the original value. That means that I didn't modify anything. So it's obvious that I'm taking to 0. You see, we have nothing because the image is completely dark. So what does it mean to decrease the luminosity? Translating that means translating the histogram, shifting the histogram to the origins of the distribution to very low digital numbers towards the 0 position. You see that we have something that you can check here. Of course, there will be values as the class here that where you can already see something, but you see that the image is completely dark. So let's reset that. The second bar, you see, is the contrast. In this moment, it's more or less 20. If I'm lowering that, you see, I'm decreasing the contrast. If I'm improving that, I'm improving the contrast. Also, in this case, I can change numerically the values and just digit the new number and pressing enter. What does it mean, improving the contrast? Is the same as stretch the data. What does it mean, stretch the data? It means if you are taking into consideration the graphics, is take the distribution bell, take the two sides and widen it to make sure that you have a wider bell distribution. That definitely means that you are improving the standard deviation of the data. So I mean, that means improve the standard deviation. Larger is the standard deviation, greater will be the contrast, bigger will be the size of the bell, of the bell. I can reset that. You see here, we have the sharpen, and these things here, that is the transparency. Sharpen is a value comprises between 0 and 100. You see, this doesn't happen anything, but we understand later on what is doing. I mean, this is a very particular operation. I'm not suggesting you to use very much, while the transparency is related to a graphical aspect. So you see, I can use the transparency, for example, when I have different images in the stacks, for example. So, for example, you see, if I open that, you see, if I'm changing the transparent, you see that I can watch what is below this image. So it's something that is completely graphics. I mean, it's not really important for our case. So these two cases, transparency and sharpen, function that to be used to be absolutely prudent in the usage of these things, because I mean, all right. What we are much interested is this to have a look at this particular menu. You see, no stretch in this case. Okay, I'm going back to this one, to the red band, the visible. All right. So here, if I'm clicking on no stretch, I have the possibility of setting a stretch. What does it mean, the stretch? From the theoretical part, is the possibility, the chance to increase in real time, because this operation occurring only in visualization is not saving anything. So we can change the distribution using the different algorithm. For example, in the linear mode here, linear with the percentage, 1% of the toes, 5%, the equalization, to force that to a normal distribution, or Gaussian distribution, or using particular other modes, or in a custom function. In this moment, we have no stretch. All right. So this data is more or less, or how it's read by the image. But if I'm going, for example, to the linear 5%, you see that I strongly increase the contrast of the image, and I'm also improving the luminosity. So I'm moving my curve on the diagram along the x-axis, and I'm also improving the dimension of the bell. I can go back to the no stretch, of course. If I'm going, for example, to the Gaussian, you see, from here, this is something that is forced to a Gaussian distribution. So you see the difference between the linear 5%. So the image is too much contrasted. Well, you see the Gaussian, you see here, it's the operation that allows to optimize the brightness and the contrast. For example, let's see, maybe on a path of Turing, so we can take it. You see that if I'm going back to linear 5%, you see that, I mean, the image seems to be very saturated, while if I'm going to the Gaussian, you see it's not so bright, but I don't have saturated values. But you see that this is really one of the best way to have this Gaussian forcing. Okay, we can go back with the reset, the original stretch. So, and we can also go to the custom option, you see here, that corresponds to what we have in this custom stretch, in this icon, you see. And this is the custom stretch. This is a very important windows, because it's basically make us see how in this moment our image is displayed. So we have our histogram, you see here, and in this case, we have activated a linear stretch that is comprised between the point, the digital number 19 and 117, that is the black point and the white point. So that means that in the theory, we called, in the theoretical part, we call minimum and maximum from a linear stretching. So you see that in reality, we have no stretch, but in reality, we already have this stretch. But this stretch is set by default in the software. Why is set by default in the software. You can understand that, because if I'm taking that to the value, to the original values, and I'm moving that to the maximum one, you see, this is the image from 1 to 200 from 0. We don't have the 0. We have the, yeah, you see, you remember that the 0 is the background value, and this stretch is related to these windows. This is the image that you have without any stretch, all right? Because on the video, on your monitor, you have represented the data that is read by the software in the original matrix. Let's close that. In order to better understand these things here, it's better to zoom out here, all right? So we have everything. So I have all these windows. So let's open again these things here, the custom stretch. You see, this is the distribution. This is the image, how it is loaded without any linear stretching, all right? All right, so if I'm moving that, you see, from here in the custom stretch, and I'm moving that things here, for example, to 21 to 65, you see, this is a linear stretch that is very, very big, in which I can basically manage the linear stretch, taking into account what is displayed on the video. You see, I can also use a linear stretch using a percentage value. For example, I can take out the 3% of the tail of the distribution on the left, and the tail of the 3% of the tail of the distribution on the right part. So if I'm using the 3%, you see, pressing enter, you see that they moved, taking out the 3% of the tails, you see we are limiting from 19 to 99. If I'm using, for example, only the 2%, press enter, you see I'm limiting from 19 to 117 as the previous function. So that means that in Envy, by default, in the preferences, there's an auto-linear stretch set to the 2%. So a linear auto stretch with the thresholds of 2% of the tails from the right and left parts of the histogram. If I put 0 here, this is the original representation. So it's set by default in order to make the user watch the image in the best way he can. So you see here, if I'm zooming to Genoa, here, if I want to use the custom stretch, taking that from here this time, so you see, this is without any stretch. If I'm taking here 2% and press enter, you see, here is the results. You see, it's much better than before. Of course, if I'm taking 0, you see, I mean, low contrasted and low brightness. And you see that if I'm taking these thresholds, it's better. This is the linear, and you see also here you have some other things. Well, you have also the Gaussian, you see? If I'm taking the Gaussian, you see. Another possibility that is improving both brightness and contrast. Okay, all right? So here, let's go. So we modify the contrast. Let's close the second views with right-clicking and remove view. And in this case, I can remove the visibility of the band 4. And you see, now we have the image in true color. And you see that the stretch can be done also on color image, of course. So if I'm going to the custom stretch, you see, I have my different histogram. For example, here, let's have a Gaussian, right? You see? Or a linear at 2%, 4%, pressing enter, you see? I can modify the stretching value. I'm sorry, but I'm using the wrong one. I'm sorry. I need to open this one. Okay, I'm sorry. It's happening. A mistake. Okay, I'm selecting this one. All right, so I'm going here. And you see that now we have the three different histograms, you see, with the three histograms that are associated to the blue, green, and red channels. So these colors are related to the channel of visualization. So red, green, and blue are related to the red, green, and blue bands in this case. So you see, we can see also separate, so the red. So I can improve the contrast of the red, you see here. So it's changing only the red. So, all right. So we have a reddish dominant value. We can do the same things with the green, all right? And the same with the blue, all right? So you see, we improved the values. Oh, in these things here, we can use, for example, the 3% linear stretching, okay, pressing OK, and you see, we have the results. Or if I'm going the Gaussian, you see this is the results. So we can use that both in panchromatic and both in color images. All right. And so that means that we can change the data distribution display using this function in real time. This is very important because it makes us aware that this data has a particular distribution. And for example, here in Genoa, where we have the runway of the airport and where we are doing photo interpretation in real time, the possibility to change, you see, for example, this is the original data, and you see it's very difficult to understand. If I'm putting a linear stretching at 2%, you see that we can observe better this data. So this is one of the first aspects that we must take into account in order to use this data, and it's extremely useful. All right? So for today, we have talked fundamentally about how we can work on the data itself, the statistical distribution of the digital number of our images, and we introduced from the practical point of view the histograms and how to using contrast stretch operation, you can modify the standard deviation and the maximum value of the distribution of the different histograms. And you see that the possibly modification, shifting or stretching of these histograms can change both the brightness and the contrast of our images. And I mean, these operations are very, very important because also in the second phase, we see that how it's important to do this operation. And in the first phase, we also saw the metadata and how these metadata are very important to understand the quality and the characteristics of the image. So let's finish at this time the fourth lab, in which we basically introduce the data that constitutes our data. So take